Understanding what we write and say is one of the main goals of most AI models. If you have used any chatbots such as ChatGPT or Claude, you have seen how fast these models understand your question and generate answers in the form of text. But we already know that these models are built by neural networks, and neural networks work with numbers, not words. So how do they actually process these words? Even before using neural networks, we have used traditional natural language processing or NLP methods to process words. In natural language processing, we treat words as the building blocks of sentences and texts. And the most important part of processing these words is to convert them to some type of numerical form so that algorithms can deal with them. This process is called word embedding. Before we delve into more technical details, let's take a look at some fundamentals of words and their properties. Consider the words king, queen, prince, and princess. As you can see, all of these words are related to the concept of royalty, but two of them are male and two female. Two of them have a higher status or rank and two lower. We can represent them in a semantic feature space, where the x-axis represents the semantic feature of gender and the y-axis represents the semantic feature of rank. Even though this coordinate system is quite arbitrary, we can use these numbers to assign arbitrary coordinates to each word. You can also think of these coordinates as vectors, also called feature vectors. For example, the word king can be represented by this vector, and the word princess can be represented by this vector, and so on. But this type of representing words is close to what we call the bag of words, or just a bunch of words, because we cannot capture their differences based on their meanings. So this remains a simplified version of how we nowadays represent words, especially when we are trying to build neural networks to solve more complex textual problems. Here's the time to recap what we learned from the previous video about word embedding for neural networks and then continue with today's journey. Imagine our input data is the sentence, "I watch all videos from analytics camp," where the word I is our first input word or x1 all the way to the last word or camps as x7. If you've seen my previous videos about how neural networks work, you know that each input data is multiplied by a numerical value called weight. But wait a minute, how do we multiply a word by a number? In machine learning lingo, this is called embedding. In earlier days of machine learning, we used to use a simple method called one-hot encoding to encode categorical inputs such as words in a sentence in numerical form. All we used to do was construct a vector with the length of the total vocabulary we have. For the sake of simplicity, let's imagine that we only have these 7 words in our vocabulary. So we have to represent each word with a vector of length 7, where that word's position in the sentence gets the value of 1 and the rest of the positions get zeros. This didn't end up as a useful solution for natural language processing, as it was inefficient to waste so much space in memory for all those extra zeros, especially with a larger vocabulary such as a million-word dataset. This method also didn't capture the similarity of words in a vector space because all vectors end up having the same distance from each other. So we couldn't capture contextual meaning with this type of vector representation. It was clearly the time to invent better ways to capture the meaning of words in a sentence while converting them into numbers. One of the earliest methods that computational linguists came up with was a method called term frequency inverse document frequency, or TF-IDF for short. Term frequency looks at the frequency of each term in a document, for example, the number of times a particular word appears in a text. Similarly, inverse document frequency captures how many times a word appears in a text compared to other text in that corpus or collection of texts. As you might have already guessed, we can use this method to find out the main topic or theme of a text without personally reading it, because we assume that we usually repeat the main word or topic more frequently than other words. This method is one step more informative about the meaning of the text, but still cannot represent the meaning of each word relative to other words in that text. For example, some words get a value of 0 because they haven't been used in that particular text, but that doesn't mean those words do not convey important meaning in another text or in the corpus as a whole. So it's time to level up, and this time linguists massively improved the method, called it word-to-vec. Word-to-vec was developed by Google researchers to capture the word associations or the meaning of words and their textual values by using a predictive model. Remember the vector space I explained earlier? In this approach, word vectors that are closer to each other in the vector space have similar contextual meaning, and the vectors that are far from each other have different meanings. In natural language processing, we have a couple of methods to assess the semantic similarity of these word vectors. Basically, semantic similarity between two words was traditionally captured by metrics such as cosine similarity, which is the cosine of the angle of the two words' vectors in a vector space. For example, the two words soon and tomorrow are more similar because the angle of their vectors is closer to 0, so the cosine of this angle becomes closer to 1. Compare this to the two words soon and late, where their vectors are pointing to opposite directions, so the cosine similarity is closer to -1. This way we can measure the distances between these vectors representing the words to determine their closeness or similarity. Now, you might ask, why find the angle of the vectors when we can simply measure their distance, for example, the Euclidean distance? The answer is that Euclidean distance measures the length of the line between 2 points. So the shorter the distance between the two words is, the more similar they are. In the earlier example that I showed you, for example, the word king will have a similar distance with the word prince and the word princess, which is not correct. But using the cosine similarity, we can see the angle between the vectors of king and prince is less than the angle between the vectors of king and princess. So this method is closer to human ideas of word relatedness. But that's not all. Computational linguists at Stanford went a step further to improve these methods and came up with GLOV, or Global Vectors for Word Representation, which combines the benefits of context-based learning in word-to-vec and the use of matrix factorization. If you haven't heard of this before, it basically first constructs a large matrix of words in context, where the rows are words and the columns are the context in which those words occur. Because the number of context columns could be very large, we can combine similar contexts to get a smaller number of features. This way, we can factorize this matrix to get a lower dimension feature matrix, so to say a matrix of words as rows and features as columns. So why do we need GLOV when the word-to-vec method was doing so well? Well, there are a number of reasons. For one, the word-to-vec method captures the immediate or local context of each word, while GLOV can capture the global context where the word appears as well, because it is based on the global word-to-word co-occurrence matrix from a text. However, both methods are based on the intuition that certain words appear together or in the same space more frequently. But with GLOV, we can capture similarities based on different features. For example, the underlying concept that can distinguish king from queen can also distinguish other pairs, such as man from woman and brother from sister. This feature is gender. In other words, with a specific feature, vector differences between these pairs become approximately equal. But all these methods were subdued as soon as Google researchers developed BERT, or Bidirectional Encoder Representations from Transformers. BERT is a transformer-based model that can embed words contextually using the self-attention mechanism along with the feed-forward neural networks. If you need a primer on how feed-forward neural networks work, I have this video for you with this link in the description. The embedding layer in BERT breaks down words into subwords by using the word piece tokenization, which also helps the model to understand more details about the words. The bidirectional part of the BERT means it extends the context to both directions, the right side and the left side of each word, as opposed to older models that used to process text in one direction, for example, only from left to right. This bidirectional feature also comes in handy for another feature of BERT called masked language modeling, where some random words in a sentence are masked or hidden from the model to force the model to understand the context of that masked word while looking at both directions. So now the model's job is to predict what that masked word was in the original text. This learning process makes the model better at understanding the context. As you can see, word embedding in BERT not only means converting the words into numerical data, but also capturing large context from both directions. I hear you saying, so what's the difference between BERT and a workable solution like RoBERTa that we saw earlier? The answer is that RoBERTa makes a much simpler prediction of the next word within a fixed window size as the context, which makes it a more static embedding, while BERT can capture a larger context including the nuances of language such as sarcasm and metaphor. But we haven't stopped here. We have a plethora of other embedding methods, such as RoBERTa, which is the optimized BERT method, as well as methods such as text-to-text, transfer, transformer, or T5 for short, and BART, or bidirectional and autoregressive transformers, all of which use very interesting architectures for embedding and representing words. If you want me to make a more detailed video about these and other embedding methods, let me know, but for now I have this very interesting related video tutorial.